Assalamualaikum and greeting everyone. My name is Nurul Najihah Zulkifli. I am responsible as corresponding author and presenter for this study. It is about state feedback controller tuning for liquid slosh suppression system utilizing LQR-LMI approach. First, we understand the slosh motion. As we can see in this figure, when a partially filled liquid container moves in a certain direction, the slosh phenomena occurs on open free surface area here. This application can be found in few industries where the system is desirable to move the filled container reach final position as fast as possible. However, this may induce an oscillating form motion which is dangerous to be handled. Therefore, a control action is needed to optimize the slosh motion angle in moving container. Our proposed technique was to design a control system in closed path that involved a desired reference signal, a plant system, and controller with feedback response. From previous works, there are several attempts have been done to optimize slosh suppression system, such as sliding mode controller for PID scheme control, H infinity, also data-driven or fuzzy logic, simultaneous perturbation stochastic approximation, exponent-based simulated karma filter, single input fuzzy logic controller. Mostly, those controllers were developed in closed loop, where it much stable and less sensitive to noise. Hence, we consider a state feedback controller tuning by LQR as controller technique system. Then this technique be modified into suboptimal LQR based on this study to optimize slosh suppression system. We illustrate our system as shown in these figures. The system can be derived into nonlinear expression as written in this function. To make it less complex and simple, the nonlinear function transforms into linear function as represented here. The state is defined as card displacement, velocity of card displacement, angular level of slosh motion, and velocity of slosh motion. We designed our control system in closed-loop path with state feedback controller and integral term control. With the additional term, this servo can be transformed into regulator control. It forms a new linear function or state space representation and formulated a new control law of U equal to Ks. Based on controller design, we want to obtain the optimal parameter gain by implementing control algorithm based on LQR-LMI approach. In this study, we compare proposed technique LQR-LMI with regular LQR. First, we implement regular LQR, which need to obtain the optimal solution that minimizes the performance index of J. We use this related control action to minimize the performance index, where the optimal matrix can be solved by computing algebraic Riccati equation with command of LQR in MATLAB simulation software. The minimum condition can be defined as this condition. Then, we modify regular LQR into LMI constraint optimization method by computing gamma bigger or equal to J mean instead only J mean. We recast LQR problem into suboptimal LQR-LMI over P hat and Y as this definition. That subjected to constraint optimization problem to be determined by LMI solver in MATLAB simulation and obtain the parameter gain of K by solving this equation. Finally, we implement integral square error to evaluate the effectiveness of LQR-LMI. We solve this equation based on output response. The result will determine the best solution based on comparison of index that reach to extreme value as this equation. To present simulation result, we properly choose metric weight of Q and R for both techniques. Also choose initial state and value of gamma. We can see the trajectory output of card displacement can be shown in this figure. Both methods generate a smooth and zero steady-state signal. However, LQR-LMI produces a faster response of the card movement compared to regular LQR. While the slosh motion can be observed that both approaches yield a small oscillating signal, although LQR illustrates a smaller signal than LQR-LMI. Thus, we analyze the performance system in terms of ISE. It can be found LQR-LMI produces a smaller value, which determines LQR-LMI is better approaches to be applied in order to minimize slosh angular motion while card is moving compared to regular LQR. As conclusion, state feedback controller with integral term in the slosh suppression control system has been developed. The trajectory of the card able to track desired position while minimizing slosh motion. The proposed method exhibits a better performance system compared to regular LQR. Suggestion for future work. Validation of the proposed method utilizing the real experimental hardware setup. Then implementation and use of any meta heuristic optimization technique as a part of tuning process to obtain the optimal controller parameters. That's all for me. Thank you for your attention.